Okay, hello, welcome. Sorry for the slightly late start. I am streaming this on CPU encoding because OBS decided at the last minute it didn't like my graphics card. Anyway, hopefully it still works. If there's a problem with the encoding or the streaming, let me know in the chat. I'll see if I can fix it. But otherwise, welcome back for more Haskell programming. So last time out, I was looking at Control.Monad.Except. I'm trying to use exceptions. Was it Control.Monad.Error? No, it was Control.Monad.Except. I was trying to use exceptions instead of always returning an either type and then having these sort of nasty nested case statements. Because as I was calling multiple functions, each one could return potentially an exception, or at least they could return some kind of error encoded in an either type. And for each function I called, in turn, I had to sort of nest that deeper into a case statement saying basically, only if the previous one was successful, try and process this next one. So I struggled last time to get everything working, to understand how to use Control.Monad.Except and the throw error and catch error stuff. And then at the end, I got something kind of working, and I wonder if I kind of missed the point a little bit. Not necessarily in Control.Monad.Except itself, but the thing that really made it easier for me was using do notation, using monadic do, because one of the problems I had was assigning a variable and then using that variable later on, not immediately, but much later on, and that kind of led to the nesting, and it stopped me just using bind on the either type. But I think that actually, in practice, the monadic do form is simplifying that a lot for me, so I can write it out in a way that's easier to read, and it's worrying about threading the variables through behind the scenes. So I'm kind of wondering if I can use that monadic do to write the functions I want to write, change all of the functions to return the either type, and then just centrally in the sort of the core of the VM have something which runs all these functions and then catches the exception. So that's what I'm going to try and do today, I think, is not catch exception in each instruction, but to catch it centrally in the CPU. So let's give that a go. I haven't looked at this code for a couple of weeks, so it's going to be fun remembering stuff. I'm pretty sure it was the return stuff I was working on last time. And in fact, here it is. Yes. So in here, I'm saying this either returns stack error or CPU, and then we did the catching stuff here. Now what I'm thinking is that this catching stuff I could just get rid of. Let's leave there. Okay, and then separate should still work in the same way. It's basically either going to return some right success or left error. And the error in this case is going to be some kind of stack error that comes from the stack package I was writing, stack module. So given that it returns this already, what I'm thinking is I can move the catch up to the place that calls it. But I can still take advantage of the sort of monadic do form to do this kind of assignment. So that would mean in the caller, so it's being called up here from step. What I might do is just write step prime for a second. And this is exactly the same signature, so we go from a program, and some kind of initial CPU state to a new CPU state. And I can have the same base case, so I can say if we have a CPU that's already in an error state, so we have some kind of error, then we just return that CPU unmodified, like we don't do anything in this function. But otherwise, so step prime, some kind of program, some CPU with some state. I guess I probably want to pull out the .p. Yes, I do. So we pull out the instruction pointer, and we can say go, and then we can put the catch error stuff into here. So when I call these instructions, when I do this destructuring, I can have them all return the either type, and I can catch it here, and then I can say if we got an error, and set the CPU error to whatever error came out of there, and then we're done, I think. So I should probably define these things again. So where instruction, instruction is pbang CPU IP. So we pull the next instruction off, and then we'll define go as being, I guess there's only one clause for this at the minute. So if it's return, then we say stepret prime, and then we pass in the CPU. And then we can say otherwise CPU, and we just set the error saying, oops, just unexpected instruction. Okay, so a few things have not worked out here. So otherwise, I actually don't want to do this. I want to say left and then some error. Okay, so the error that I return from here is going to need to be the same as the error I return from here. And the error that I return from here is s.stack error. So I maybe want to create some I guess maybe another module and put all the errors into there. The reason I'm saying another module is because I can't import, if I define them all in the VM, I can't import it into here because this is imported back into VM, so it'll be a circular dependency. And if I define it here, I'll be defining things that are only used by the VM inside here, and that wouldn't feel right. So let me just go to the compile file quickly. Library VM, and we'll write something called VM errors. And we'll just create that. VM errors. Say module VM errors where. Now I'll just grab this. What else could we do? So those are stack errors, and then we could say data. How would this work? You have VM. The trouble is they all need to be the same. So I maybe need to make some superset here, so we can say empty stack. Or stack too small, or invalid stack position. You can all derive show. Okay, let's do that. But the other thing it could be is something inside the VM, so we could have what was the thing I was thinking? It's unrecognized command. It's not instruction, not command, it's instruction. So unrecognized instruction, and I'm going to pass in a word 8 to this because that's what the instruction type is. Yep. and I can just export this. So export VM error dot dot. Okay, so we go back to stack, and I will not find the stack error here. And I'm not going to throw a stack error here, I'm going to throw a VM error. And hopefully, control dot, sorry, I import that. Then I don't export stack error from here. Right, okay. Then we can just add these to the imports. Is that the only one we have? Empty stack. Okay. Back in the VM, we can change this to be stack error. No, VM error, sorry. We import that. And this is also going to return some type VM error. I could probably get rid of this type signature now, because I don't think it's particularly helpful anymore. And in fact, because I'm not catching it, I could get rid of go as well. I could just change this to say do. And just have that inlined. Okay. So, pure in this case, I think, is returning the CPU as a write. Pretty sure that's what's happening. Okay, so we go back up to here. We can throw unrecognized. Well, let's complete for me. Unrecognized instruction, and then we can pass the instruction. And this whole thing should be left. Okay. Instead of left, we could say throw error, I think. Which is the same thing. I think it just makes it a little bit clearer, maybe. Undo that. One there, throw error to that. Yep. Okay, now we have a problem because we said that step returns CPU, and this is actually returning left. So I can get rid of pure at this point. Now the type of this is different from the type of go, because go will return return to neither type. So maybe here, instead of using catch error, I'm going to say case go of, and then we say left error, and return that. And we don't need a lambda there. You just return that CPU. And we can say write CPU, and then we just return the CPU. And this is the error. And I'm surprised it didn't offer to rewrite that for me. Because I think you can say from either, or maybe you can't. Maybe you can't say from either in Prelude, sorry. Can you say from either? Can I get type for this? I cannot. File example. It's fine. What's the type of from either? It does not exist. Find a browser window. Okay, I want to go from. I think I want something like a default case and either a B and returns a B. So from either does exist but not in Prelude. Oh, thanks, Nicholas. I'm glad you like the videos. From right, well, I guess if I change this to be an A to an A, I'll delete that. What's it doing? I can do from left. So from left turns left value or default value otherwise. Oh, that's not really what I want, because I want to use the B to generate the new CPU. I want to use the error case. It would be from right actually rather than from left, but I want to use whatever is returned in the error case. I will use that to generate the value of B. So I don't think I can use that. So that's probably not what I want, but this approach I think should be correct. Okay, so what we're going to do, we could write a very simple test for this just to see if it works, but it's getting past the compiler. That's better than I expected, I guess. There's a nicer way of formatting this. It seems to let me format like that. I'm not sure it's any better though. Okay, so VM test. Here I can say something like describe. I'm describing here. I'm describing. I'm going to describe just return, I suppose. Or maybe return error handling. So we can let program, and then we need to set everything up, don't we? So I'll set up some program, but I'll make it simpler. We can just we need to do some kind of call and then some kind of return. So we won't have anything on the stack. Let's not worry about that. I'll need to implement call, I guess. So this is 0, 1. I can get rid of this. So we'll have call, we'll have the destination of call, and then we'll have halt. And then we'll push something on so that there's something to return, and then we'll just call return. This might help track down the problem I have in return as well. In fact, even before I do this one, let's just do error handling general. Let me just find run. So we're probably going to write a run prime. This one program to a string, and then run prime p is it's the same thing. I'm just going to replace step with step prime. I scrap all these lines, probably easy thing to do. So run prime p is this, but it's going to call step prime. What's this? Oh, am I writing a generic CPU emulator with support for any arbitrary instructions? Okay. Yeah, so what am I doing in general? I'll finish writing run prime and I'll come back and give a recap on what it is I'm building. Run trace, I'll just stick in here, run prime. And back here, I'm just going to say it errors on unrecognized instructions. And then I can say vm.run and we'll give it some nonsense program. So we'll just say let program is from list, and well, actually the only thing I've implemented at the minute is return. So I did vm.push in here, vm.run program, run prime. Should be, and then what does it do on an error? That'd be good to know, wouldn't it? It's the error itself, so it's the string version of my error. So it'll be unrecognized instruction. Unrecognized instruction, in fact, just to make life a bit easier, I will not try and guess what she'll will print out. Oh no, we'll try and guess it. Unrecognized instruction, and the instruction code is push, wasn't it? So I think it's just going to say 1. Just going to run this. I'll come back to recapping. Subscribers not scope. Okay, it didn't tell me that, which means that the language server is probably broken. Can I restart? Yes. And that. Okay, try it again. Oh, it's running, but it's stuck in its infinite loop. Let's just kill that. Okay, there is something wrong in here, I think. Let's try that again. Oh wow, no, that was not the problem. Okay. So the problem, I guess, is in the termination of this loop, this until we don't hold. Right. If we get an error, we should hold as well. So CPU halted is true. And we have an error. Does this not work? It does not. Okay, let's come back to him in a second. Right, so Andresh, what am I writing? I started off wanting to look at how stack-based VMs work, or just how a stack machine works. And I wrote a very simple calculator. So we gave it some input string. There's a simple parser for this. It turned it into a list of, I guess, operations. There was no VM executing it, but it would just convert it into a list of it basically just reordered this into reverse Polish form. So it would turn 1 plus 2 into 1, 2, and then plus. And then I just wrote a very simple interpreter for that, which went left to right, and it had a stack for keeping the result. So the 1, 2 plus would be validated by pushing 2 onto the stack, pushing 1 onto the stack, pushing 2 onto the stack. Then you get to plus, and you pop the last 2 things off the stack and add them together, and then push the result onto the stack, and then that's what we return. So that's what I wrote originally, but that's super limited, right? It's not very exciting at all. So then I rewrote it using a stack-based VM. So this thing, and we now have a parser, and it spits out a program. But the program is a series of bytecodes rather than the original symbols that I gave it. So it has a very small instruction set. It can halt, which stops processing, but we can also push stuff onto it. We can call and return functions, which is the thing I've been working on for a couple of weeks, but it doesn't work yet. We can add numbers together, subtract them, and multiply them. So it's a similar idea of being able to have a very simple calculator. I guess this would support functions as well. And then we run it through some kind of bytecode VM, which is what this run is doing. What the run is doing is basically taking a program and stepping through it until something halts the CPU. So you get this instruction called halt. And the implementation of all of these instructions are generally just updating the CPU state. But the CPU contains a stack. So the same stack-based idea is still in here. So it's a stack-based bytecode VM. Internally, it's using a stack to push stuff onto and to pop stuff off when it needs it for operands for some kind of operation. And it pushes result onto there. So I hope that kind of explains what I'm doing. It's not a generic CPU emulator. It's much smaller than that. It's a very simple stack-based VM. At the minute, my compiler doesn't exist. The parser does it spit out bytecode? I can't even remember if I've done that yet. I think there's a little bit of bytecode generation, but I haven't written the compiler part for pushing and calling yet. And what I'm trying to do is get call and return. I'm trying to get those working just by manually writing out the instructions and running it through the VM. And when I get that working, I need to do a little bit more to support parameters. And when I have that working, then I can look at the compiler side of this. So how do we take like a function definition and turn it into the relevant bytecode? Yeah, cool. Okay, so that's what I'm trying to do. I'm not making rapid progress, but maybe that's fine. Yeah, I had this test that was spinning forever. I presume it's this one. So if I take this out, let me just undo all of that, sorry. If I take it out in one go, and then also fix this, and run the tests. I'm hoping the tests will... Oh, they're still stuck running forever, so it's not my new code that's the problem. Okay. So let me put it back in again. If it's not that, then it's possibly this one. So it's function calling, which is probably stuck forever. I think it's just a hunch, but I think function calling is the one that gets the error and doesn't fail, doesn't halt. Okay, cool. Okay, we got a whole bunch of stuff because nothing works anymore. But VM error handling, errors and unrecognized instructions. So this passed, which is cool. Okay, I'm probably going to have a failing test for quite a while now as I piece together the VM. But one error I'm interested in is we have unrecognized instruction, and then there's a thing around it called return. Is it return and the stack is empty? Let me just look at how return works. It has been a while since I wrote this. So what's this doing? When you call return, it pops the stack to get the result and the remaining stack. So if your stack is empty and you call return, there should be an error. Then it pops again. I'm just going to try and remind myself how this works. So I think the way that call works is if this is a stack that we've got, we have some stuff at the start of the stack, we don't really care what it is. When we get to call, I think I could probably go and look at the definition call and see what it does. When we get to call, it takes the call address, and what does it do with it? The call address becomes the new stack point, the new instruction pointer. That's not that interesting. The stack pointer gets set. Okay, so we're going to remember that our stack starts here. And then we take the return address. So if this is the stack. We also have the program, which is just a list of stuff. So you might say call is your first instruction, your first byte, and then the second byte will be the destination you're going to call, the place in the program. So this might be, let's say it's 7. And then you got some other stuff, and then eventually it's 7. This is where your function starts. So the return address will be this point. Right, we've got to remember we're going to pick up after we've processed the call instruction. So this will be position 2 in this case. So we're going to take 2 and we're going to push it onto the stack to remember where to go back to. And then at the moment, we don't support parameters. So typically I would probably put the parameters at this point, but I don't have parameters yet. Then we do whatever else we need to do in that function, pushing stuff onto the stack as necessary. And then at some point, let's say we have value 14 for no particular reason. Let's imagine that that's what we end up with as a result of our function, and that's what we're going to return. What we then do is we take this value 14, I'm just going to change color here, let's change to orangey. We're going to take this value 14, we're going to remember it as a result. Then we pop the stack. And what that means is we're going to take all of this stuff and we're just going to delete it. So we're basically winding back our stack. We're then going to pop this, and this is going to become our new instruction pointer. So our instruction pointer went over to here for the function, and now our instruction pointer is going to be set back to here, which is the return address. And then we've popped this off the stack to find it. So the stack is now back to exactly the way it was before we called our function. Then we take result and we push it onto the stack. Okay, stack is filling left to right, so pushing onto stack pushes it onto the right hand side. So that's what we're trying to do when we pop something off. Okay, so if we call return with an empty stack, it's going to try and pop the result off, and that should just fail. Right, if we call pop with an empty stack, it should throw empty stack. So in the test, so inside here we could maybe just write a whole thing for return. So it errors if the stack is empty. So you can say let program is from list, and then vm.ret. No, vm.ret. It is ret. Okay, cool. So program is that, and then we can say vm.run prime or program, and that should be, and then the string, which is empty stack, I think it was. Okay, run that test. Up here, yep, it errors if the stack is empty. Okay, and just to, well, I guess another case, so it errors if the stack does not contain a return address. Doesn't matter what the return address is, I guess, to some extent, but we can say I guess I'm really saying it doesn't work if there's only one value on the stack. Oh, how do I control this? I want to say it's a bit of a nonsense program, but it's okay because I can just write the instructions. So we're going to push the value 2 onto the stack, and then we'll call vm.return. And this should also give us empty stack, because at some point during the code for returning, it'll run out of stack. 6 failures. Okay, this is not the case. So errors not return, contain return address. Or we get unrecognized instruction because I've not implemented push yet. Okay, let's write a definition of push which satisfies this. Okay, so back in the VM, in our run prime, we'll add the handling, step prime. We'll add the handling for pushing stuff. So if the instruction is oops, push, then we're going to call step push prime. At some point I'm going to get rid of all the prime bits, but let's do them instruction by instruction. And I'll just copy this. Actually, will I copy it? Let's just call it. Might be easier than copying it. So step push prime, get some program and the CPU to either VM error or a CPU. And this is really boring, but step push prime is just, no, it's not just, it's write. I can write pure, it's quite fun, I think. I can write pure at this point. Might be in a do notation to write pure. I can't write that. I can write right. I can write right. No. I thought that would just work. So program the CPU is right of step push takes the program and CPU. Why can I not? Why can I reduce this? I want to go 0.3, damn it. So right after step push, apply to this. And it says I cannot do that. Okay, let's just leave it at that. Okay, so definition of step push is just calling the original and then effectively lifting it into this either monad. Pushing is just doing its normal thing. There's nothing go wrong with pushing. Or our virtual machine is infinitely large. So if I rerun this, I should get down to 5 failures again. Didn't work. Oh goodness. Index out of bounds. Ah, okay. That's interesting. So I'm guessing it actually gets slightly further. It's a very confusing stack trace, I think. So if I go back to the VM, what I think is failing is something inside step ret. This version. Just for comparison, actually, this is the version I'm working on with the either type and throwing and catching exceptions. And this is the version before with the nested case statements, which is just, I find very hard to read. Okay, so first of all, our program consists of pushing and then the value 2 and then returning. So pushing and then the value 2 at this point, when we call return, the stack will consist of a single value, which is a value 2. So if we call pop on the stack, that should give us back the value 2 and then an empty list. And then we call pop again. And I think it should throw empty stack, but it doesn't seem to be throwing empty stack. It seems to be doing something else. So I call it empty stack, it should throw empty stack, and we've seen that work before. We got a test for that. And we call it anything else, then it should just pop, right? It should be totally fine. Maybe it's not that bit that's broken. We haven't finished writing step rec, so we don't have the stack pointer. We don't have the IP. Okay, we haven't implemented the whole thing, but that should make it less likely to break. I mean, it won't. It's not a full implementation of return, so that won't work. But it shouldn't break in the way that it did. I mean, I don't understand why it breaks. Sorry. So index out of bounds. Oh no, hang on. Because we are not, because we haven't finished implementation of this, it's actually getting past this that we call pop on here, and this fails, I think, but we don't have halt. So what I'm thinking happens is we push the value 2 onto the stack, we call it return. That actually works because it's not a full implementation of return. It should break, but it doesn't. And then it tries to do the next instruction, and the next instruction is not there. And that's what's breaking. So if we do vm.halt, we're not going to get an empty stack exception here. We're going to get an unrecognized instruction 0, I think. Let's find out. No, it's not that one. VM error handling, errors on unrecognized instructions. Oh, it's nothing to do with this. This does return the right problem. I should have read the full error message. It's this now, because this is implemented. So it reads this, it tries to get the next value out of the operand to push onto the stack, but it can't get it out because there's nothing else in my program. Okay, so I've fed it some invalid bytecode and now it's noticed. So we can give it something absolutely nonsense. So we can give it nonsense is not XF. Then we'll export that. Okay, it's written not XFF, but I like the idea of keeping the definition of every instruction here, even if it's an invalid one. Right, so I can say vm.nonsense. And this should be 205. Look at that, back down to 5 failures. Okay, so these all work. Okay. And then we can say it errors. What's the next guess I can do for return? I mean, it should error if the return address is invalid. But now I'm getting deeply into the implementation of the stack. So the return address is the thing after the stack pointer. So I need call for that to work. Let's go back to here for a second. I'm trying to do some of this nonsense. Can I do it? I should have done layers, it would have been so much easier. Okay, it's this daily. So this is the stack pointer inside the VM. So initially the stack pointer is going to be here. Maybe I could rely on that, but it's not guaranteed behavior. I think initially the stack pointer is unreliable. And then when you encounter call, this stack pointer moves to, well, the stack pointer gets set to the current location. And in fact, I think looking at implementation of return, I have a suspicion. That return works by pushing this, which is return address, and then setting this to be the stack pointer. Because I think what happens is you pop all the way back to here, and then you pop again. I think that's what it's doing. I can maybe have a look at the implementation of call, I suppose. So step call, what are we doing? We're setting the stack pointer to new stack pointer, which is s.position position of new stack. What does even that? What does that mean? New stack is okay. Yeah. So new stack is whatever the old stack was, with the return address pushed onto the front of it. So we push it onto the front of it, and then we take the stack pointer after that. So yeah, I think it's what I suspect. It's that the return address is the thing before the stack pointer, not the thing after the stack pointer. That do? Oh, position just works it. Okay, because the stack is a simple list in Haskell. The position is actually the end of the list, which is just however long it is, and then we're pushing stuff onto the end so that we can easily jump back again. Okay, so if I write this properly, then we can get the result. Thinking about it, it's just the last thing in the CPU stack. And we only want result. We don't actually need to remember what the rest of the stack. We're not going to use that. We can just chuck it away, because we can then call this kind of pop thing, or we can call return. So we pop once to get the result. We then use return to jump back to the previous stack pointer. And that's going to return me something. I think it's just return me a new stack. I think, because we want it, all we want it to do is throw away everything else in the stack, just go back to where the stack pointer was. So return is actually going to be some kind of jump to. Can we just say jump to? Actually, we have a function called ret, so we can just use that for a second. And then we can use CPUSP and then the previous stack. So we can call this new stack, or popped stack, or returned stack, or original stack. So I'm going to call it, st. Okay, now the return address we can call it s. The return address is going to be the thing that you pop off the stack after you've returned. So in that case, I could say we'll return it here. So return address, and S is what happens when you call return, passing in the CPU stack, sorry, the stack pointer, the point at which you want to return to, and the CPU stack. Okay, and then when we get through all of that, we can say our CPU is equal to, well, the CPU stack is result pushed onto S. So the result we captured up here, we push that onto whatever is left after we finish popping. And then the CPU IP is return address, this thing we stored before, and the CPU SP is 0. This is unsafe, so we'll need to also get the previous stack pointer. Let me just leave this out for now because 0 is the wrong answer. Okay, so now I just want to write rep prime and then I'll call it a day. So rep prime is going to take an int, which is the position that we are jumping to, back to. It's going to take a stack, which is the current stack, and it's going to return either a VM error, or it's going to return the pair containing the return address. Oops, that's going to be an int. At the minute, my stack is a list of ints. So I'm going to return return address and the new stack. The rep prime, some position. Oh, I need all this nonsense. Okay, so what we're saying here, we're saying if we have a stack with at least one thing on it, what's this doing? And what's this other case? So if we have an address to return to and a stack called S that contains at least one thing, we don't care what the other things are. Then if S, the length of the stack, the whole stack, is greater than P, that is, P is less than S, so P is somewhere else, somewhere in the stack. Then we return this. Okay, we need to do a bit more work here, I think. Otherwise, we return left, and there's some code for this, which is like invalid stack position. Okay. Otherwise, we can't return this, but we can return left. No elements on the stack. Is that oh, no elements on the stack will be empty stack, I guess. Okay, so now we just have this to worry about. So we have I want to pull out the return address as well. So let me just change this to be jump. Okay. and this is just going to return the stack. Okay, and then ret prime it's got this type, except that now we have the return address in there as well. And ret prime is going to be pop prime, or is it pop? We got something called pop prime. Pop prime, and that's going to be applied to jump. I can't do this. Pop prime. So here we have an int, which is some position, stack, which is s, and then it's jump of p and s. Oh, okay, what do we feed into pop prime? We feed in a stack, and this is not a stack, this is either VM stack. So what I can do is, I think what I can do is just use bind. Just use bind, but okay. So type of this is basically A to MA. It's very complicated, A to MA, but A in this case is stack. Or A to MB, sorry. And MB, the M is the either type, or either VM error, I guess. And then the B in this case is int stack. And then we got either VM error and stack. So we basically take this and lift it into this. I think the way bind works is that if we have left, in this case, it just doesn't run pop. If we have right, we take the value of right here, which is a stack, and we feed it into pop prime. Let's see. And this is called ret prime. Okay, I need to desugar this a bit. So CPU stack and CPU SP, not desugar, destructure, sorry. Okay, so we have our CPU pointer, stack pointer, and we have our stack. We get the result out, we get the return address out, and then we return to it. So the test I was writing for this was if it errors if the return address is invalid. And now we can set up, well, setting up is a bit more difficult. I'll have to implement call as well. And I might wait till next week for doing that. But I basically want to say vm.call, we'll give it some address. Let's give it the address of 3, I guess. So this is instruction 0, instruction 1, instruction 2, which will be halt. So we should come back to this point and then just halt. And then this is my function. So my function can be really stupid. It can say vm dot that thing. We can push 3 onto the VM, and then we can say vm dot ret. The trouble with that is it's not invalid. So vm.ret making invalid really hard because I need to stack pointer in place. So I don't think I can do this. This would be the VM misbehaving, so I can't test it from the outside. And I can say it just works. And this should just be the value 3, weirdly. Not weirdly. But it's the thing they return. Here, let me just change this to a different value just to make it clearer that it's not related to the call address. I don't think this is going to work because I haven't implemented call. So it should just error out at this point. But it does not. Okay, it runs forever, so there must be a... I haven't implemented call, so I'm kind of curious as to why this is spinning forever. Interesting, it's not halting properly. Okay, anyway, I'll come back to it next time. But it feels like the pattern for the error handling is emerging. I think I'm quite happy with this kind of this do notation, doing various things, calling throw when something goes wrong, being able to call throw from stack and have it kind of propagate up here through the either, and then catching it effectively up here. I think that's working out okay. I might change my CPU error to be the VM error rather than showing at this point. So this is the detail. Cool. It is taking shape. I will come back to it next time and keep fleshing this out. Keep trying to get call and return working. I'm away next week. I'm on holiday, so I'm going to take another week off. But week after that, which is, what's day today? 29th. There's something of October. No idea it's work. But yeah, not next week, but the week after. I should be back and I'll pick this up again and try and get a little bit more working. So thanks for watching along. I hope it was interesting and hopefully see you all in a couple of weeks. Cheers. Goodbye.